Okay, let's jump right in. If you give one of these large vision language models a really complicated chart, think of a spaghetti graph with all these fine overlapping lines, it often gets tripped up.
Hmm.
It just misses tiny but crucial details, like one thin line crossing another or a subtle change in a curve.
And that single visual mistake leads to a massive reasoning error. It's a fundamental perception failure.
So what was the old fix for that?
Well, the standard approach has been pretty brittle. We'd try to patch the failure at the very end, during inference time.
Using external tools like cropping or masking parts of the image.
Exactly. But those are so rigid, they're scenario specific, and frankly, they just add a ton of computational overhead. We needed a solution that makes the model inherently better at seeing.
Which brings us to our deep dive today, Bi-directional Perceptual Shaping, or BiPS.
Right.
This is a framework that aims to internalize that fine-grained visual perception right during the training process.
And it gets rid of the need for those clunky post-hoc tools. The results really speak for themselves. BiPS boosted the base model Qwen 2.5 VL7B by an average of 8.2% across 8 tough benchmarks.
And it generalized well, which is key.
It's crucial. It means the model learned a fundamental skill, not just how to answer questions about the specific charts it was trained on.
So the really interesting part here is how it works. BiPS isn't a tool you use later, it's a training signal.
It is. It works by training the model on two complementary views of the same image. It sets up this kind of push-pull dynamic for learning.
Okay, so what's the first view?
We start with what's called the consistency stage. For this, we use an evidence-preserving view of the image.
So you take the complex chart.
And you keep only the regions needed to answer the question, masking out all the distractors.
I see.
By forcing the model's prediction on the original image to match its prediction on this cleaner view, we're basically teaching it where to look. We're aligning its attention with the supporting pixels.
But hold on, what if the model is just, cheating? It could still rely on text labels or context clues to get the right answer, even if it didn't actually look at the right line. How do you prevent that?
That is the perfect question. And that's exactly what the second stage, the separation stage, is for. It's the cheating test.
Okay.
We flip the script. We introduce an evidence-ablated view where we go in and precisely remove that one critical piece of evidence.
When deleting a T data point on the graph.
Or erasing the specific data line completely.
Well,
now, if the model gives the same answer when that key evidence is gone, we know it just took a text-only shortcut.
So you punish it for that. You maximize the difference in the answer between the original image and this ablated one.
You got it. It forces the model to actually rely on seeing that fine visual evidence.
So it's this brilliant duality. You pull its attention toward the necessary evidence while also pushing it away from ignoring the absence of evidence.
But that whole process really hinges on one thing: being able to generate those two views perfectly.
Right, because crude pixel-level masking just won't cut it for tiny, irregular things like intersecting lines on a plot.
No, if your mask is too coarse, you either leave in distractors or you accidentally erase important context.
So what made the data generation for BiPS different?
It uses what they call a programmatic data pipeline. So instead of trying to paint over pixels, it goes to the source.
The chart source code.
The source code itself, like the raw ETD data that defines the chart's structure. Every axis, every mark, every legend is defined by code, so we can edit that code directly.
Which gives you surgical accuracy.
Semantic control. We can create those preserved and ablated views with perfect precision, even for those tricky line intersections.
And the data efficiency here is what's really incredible. It was trained on only 13,000 chart samples.
Which is tiny for a VLM.
And it's still got a plus 7.3% average gain on the chart-specific model.
It really proves that if you enhance the core visual grounding, you can acquire robust reasoning skills in a highly efficient way. And when we tested it, it didn't just work on charts. It generalized smoothly to unseen tasks like MathVista and MMStar.
So it wasn't just overfitting.
Not at all. It learned a real skill.
Connecting this back to how the models learn, does the order you teach them these two things matter?
It absolutely does. The research was clear that the sequential curriculum, so consistency then separation, was much better than training them jointly.
Why is that?
It suggests you have to establish a stable, evidence-aligned policy first. You need to stabilize the answer, and only then can you introduce the stricter grounding constraint that forces the model to justify its answer visually.
That idea of structural alignment really is the key. In the case studies, you see the base VLM just hallucinating curve crossings or falling back on numeric priors it sees in the text.
While the BiPS model correctly traces the visual evidence to get the right answer.
So, since this enhanced faithful perception is so obviously key to better reasoning, it leaves you with a final thought. How else could this bidirectional shaping principle be applied? How could we use the same push-pull method to stop AI systems from relying on superficial patterns when they're dealing with audio or temporal data or even spatial processing? How do you force a model to see less but see right?